giving a presentation here on our robot electrical using the 2022 robot as an example here. And really what this is about is a training video to show how to wire a robot, particularly emphasis on the connectors themselves. So for our agenda today, we're going to go over the anatomy of the robot, looking at how its electrical aspect is, and all the elements that are required to build our robots. Then we'll talk about what we mean by robot electrical and go over issues with wire, connectors, and crimping, and then talk about what we do with the Robo-Rio, how we break it out with the Spartan board and how it's been evolving, and then end the talk with how we look at the battery, how we've been analyzing it, and issues that come with the battery. Here we are.
Yeah.
Okay, so go ahead and...
So my name's Het. I am the electrical lead this year. I'm a student, and I've been on the team for 4 years.
Yeah, I'm Scott Westbrook. I've been mentoring the team since 2012, so this is approaching my 11th season, I guess, or even 12th season, I guess. So I've seen a big progression. We used to be in a different part of campus in a small triangle room that we shared. Then we moved to a portable near here, and then that got destroyed to make way for this place. And we were in another portable during construction. That was the third location, and now this is the fourth location we've been since I've been mentoring the team. Okay, let's go over the robot.
So the robot has a few major components, as you guys are probably all familiar. There's the main breaker, which is the main on-off switch, which is right here. For this robot, we put a little 3D printed guard, so that way it wouldn't get hit by balls. Previously it was Lexan, which we bolted underneath it, but then that snapped off. We made this using our Mark IV printer, and the filament is on it. Our PD board is right here next to our Rio. It's open simply because there's not much that can actually get broken off of it. We use VHB to stick it back onto the belly pan, and instead of putting just the raw wire into the Lego slots, we use ferrule crimps using these. These are called ferrule crimps. They're basically circular and fit on top of the wire. And it's just a convenient way to manage the wire. We haven't used the PEH this year, so we're still using CTRA's PD board. We use the Robo-Rio 2 because our software takes up too much RAM and the Rio 1 doesn't support it anymore. We use the Spartan board so that way we can use friction fit connectors. It's really convenient. They don't get pulled out as easily. We've revamped it and we'll talk about that later. Our radio is on the opposite side of the robot. The radio is right there. We power it over PoE and over the barrel connector. The redundancy helps, and it's also legal by the rules. We use a standard radio. It's not that complicated. For our switch, we did something a bit special. We took the basic neck gear switch, we popped it open, desoldered the switch, like the little on-off switch, and then took out the barrel connector, and then soldered in 2 wires, and then put it back together. What this allows us to do is remove the complexity of having the barrel connector, and it also just makes it a lot more resistant to shock and wires getting tugged. And it's powered off of the DRM, which we have right here. You guys probably know what that is. We use that for only for the switches, the switch and the radio. All of our custom electronics have a power board that we designed that has a buck and boost power converter from 12 volts to 5 volts, which the Pi's run off of. This just allows them to run off the power directly from the PD board and reduces strain on our VRM. All of our sensors, which are mostly beam brakes, and on this robot we have beam brakes, we have optical encoders, we have POTS, and we have magnencoders. We use SRX magnencoders from CTRE. We use We use these industrial beam brakes. I don't remember their exact name, but we use two kinds. We use the red light kind and the infrared light kind. That's what these little reflective patches here are for. They basically reflect it just helps with efficiency, and also we don't need to worry about configuring this too hard. And the incremental encoders we use are mostly on the drivetrain itself. What this allows us, we don't use any other sensors on the drivetrain because we don't really need any. And we use a pot and mag encoder combo for any of our zeroed subsystems, like the intake arms or the catapult and the turret. So the pot gives us a 0 to go off of, and due to the way how the mag encoder works, it gives us a precise incremental position, which the pot does not. And that sensor combination allows us to know where each subsystem is at a point in time accurately, which our control systems need. We don't have much CAN going on this robot. We just have the intake rollers front and back, the PD board, and the flappy arms here. That's just because they don't need a control loop to run them. It's just on off. We don't have, our control loops can't run with the latency that CAN has. So that's why none of the actual important subsystems like the catapult or intake move or turret are powered using PWM. And we have some custom electronics, specifically the 4 Raspberry Pis and the IMU down back here. The IMU is kind of hard to see. It's the big black box. You guys can come up and see it after the presentation. We custom made the IMU because oh dear. Well, we don't need the presentation, but we custom made the IMU because we needed a higher precision IMU than that was currently on the market. And we put a microcontroller on it, specifically the Raspberry Pi Pico, so that we could package info from our incremental drivetrain encoders and the IMU itself and send that out over SPI to a Raspberry Pi, which is right here. The Raspberry Pi has a custom power board on top, which allows it to just take raw power from the PD board using ferrule connectors, kind of like the CAN connectors in the Rio. And what that allows us to do is just plug in power from anywhere and not have to worry about getting supplied power from the VRM. The few other custom electronics we have are the LED boards. That's what goes around the cameras. What that allows us, you guys probably have seen this in matches, is the bright green light. We don't use limelights. We made our own. Debatable design decision, but basically these are really powerful LEDs, and it has its own power controller. And it just does limelight things. Yeah.
Okay, so what had been here was describe all the elements we have on the robot. But the elements are things we, in most parts, we buy, except for the custom electronics, which we build separately. But once they come on the robot, what we need to do, of course, is wire them all together. And when it comes to wiring, we're using off-the-shelf Ethernet cables. We don't attempt to make those connectors. But everything else, power or signaling, we cut the wires, strip and crimp them, and put them in housings as appropriate. And as time has gone on, we used to do more soldering. Now we're doing more crimping and less soldering. Okay, so we'll go over the wire. So wire gauges, it's interesting because intuitively you think of the smaller number would be smaller wire, but the way the standard was developed, the smaller numbers are the bigger diameter wire, the larger numbers are the smaller. And the reason actually this came about was well before they actually used wire, I think, for electrical needs, but the higher number meant they had to draw the wire more often or stretch it farther in order to get the smaller diameter. So the number reflected how long they were stretching it, in effect. On the robot, we use 4-gauge wire for the battery cables. That's the largest we deal with. And we started out with sort of low stranded wire. It was very stiff, and even the 6 gauge you get from First is relatively stiff. Then we started using welding cable, and that's a little more flexible. Then we came across this high-stranded 4-gauge wire that's real flexible, and this is what we use now. So I'm just going to pass these things around. And you can look at the ends too. You'll see some are soldered, some are crimped. So then as we've gone on for motor wire, we use 10 gauge or 12 gauge for the motors, and then finer gauge for the low power elements, 18 gauge and 22, 24 for signal wires. With the 10 gauge, we've been using the zip wire, and this year we've moved on to, this is actually called echo wire, but it's the same gauge even though it looks a lot smaller, but the insulation itself is smaller and it's lighter. And we had to use it because our turret requires this umbilical or vigus track, and so it needs to be really flexible, and we also have a lot of cables going through it. We have like 4 Ethernet cables, we have several motor cables, as well as signal cables. And so this is just to show how we have evolved on. I pass that around too. We also use shielded cable for our signals, and I'm going to pass around a 2-pair cable and a 6-pair cable that's shielded. It's not clear how necessary the shielded wire is anymore, but we've been careful with our sensors, especially the analog ones like the pot, which is an analog signal, to make sure we don't get motor noise into the signal and then throw our software off. So I just pass something more around for you to handle. Okay, so we have strippers to use for the wire. This lower one, which I actually didn't bring one here, but it allows you to strip multiple wires at once, or either a bigger gauge, so it can be quite convenient if you can make it work okay. The other is a little easier to handle manually. And for our battery cables, the contact on the far left is what we use in the Anderson cable, the battery connector itself. The middle one is what we're using to connect the cable to the PDP board. And then the one on the right, that connector is what we use on the battery itself. Okay, you'll see a picture of the battery later in the talk, and you'll see where that ring terminal is being used. And to do the crimping, we actually use a hydraulic crimper for the battery cables. It gives, the mechanical advantage allows you to get a lot of pressure on the crimp and make a good connection, a good mechanical connection, so if even people pull on the battery wires with the weight of the battery, you don't pull out the wire. Okay, so as I mentioned earlier, we used to do soldering. We used to solder the wire, the battery cable into the contactor as well as the ring terminal. Kind of gone away from that for a couple reasons. One is the solder tends to wick up the cable itself and makes it really stiff. It's leaded solder, so I guess there's a toxicity issue too, of course, but and on the robot itself, it adds extra weight too if you use a lot of solder. And with the hydraulic crimper, what we're doing on the left, with a good crimp, we're getting good enough mechanical connection anyway, and it's as good as electrical connection you can get with the solder.
Yeah, so these are the Wago connectors that we use, these are the ferrules that we use. I showed them off earlier. They each have their own sizes that they can fit in, and normally you could use wires that are just you could just use the plain wire brush, but putting them into ferrules makes them a lot easier to handle, and they don't hurt you. They don't randomly touch each other when they're right next to each other. We use this for our can. We use this for power into the pies. We use this for basically anything that goes a long distance and needs to be hot swappable. Can you go to the next slide? So this is how we crimp it. We have two ways of crimping it. We have the square crimper. The main advantage this one has over the circular crimper is it makes it flatter and it can fit into those tighter connectors like on the Rio a lot more easily than the circular version. The circular version is just easier to use because you know how far you're going in, and it's good enough for most of the Wago splices that we use. So these are the Wago splices. They're really neat. If you guys have seen the PDH, it just has blown up versions of these. They have little snapping connectors which fit the which fit the Wade Millers or barrels. We use this for our can. We use this for basically anything. They don't come out, but it's really easy to pop open and take out the ferrules. They go on basically any wire. They also sell 12 gauge versions in case you want to Wago your motor wire.
Why don't you pass the tools too?
Oh, yeah.
Yeah, so we'll use low power with the Wagos as well as can and signal extension, especially on the robot. We like to be able to disconnect certain subsystems, so the Wago allows us a point of disconnect. So if we have to repair something during the competition, we can do it quickly without having to cut wires and reconnect.
You go to the next slide.
Okay.
Yeah, so this is a blown up version of what's on the side here on our turret. Our turret has a lot of Wago connectors right here because we have a 3-pair cable coming up with all of our PWM and our can, which allows us to, it makes it really easy to swap out motors and also verify that the cables themselves are functioning. For example, this here connects a motor cable to our candle, which is the status light all the way on the top. And it also helps in case you want to, like, for example, take out something from your can line, or if you want to verify that another motor works by just plugging it in, or if you want to, for safety reasons, disconnect your climber, you just pop out two and then take out both of them. These are Anderson connectors. They allow us to do most of our power. They're designed, we mostly use them for our 12 gauge connections. We don't use them for lower gauges. It's these. You guys have probably seen these before. They plug into each other really nicely after you put crimps in, and they're just neat to use. They also snap together. So let's say you had like 3 motors that were right next to each other and you didn't want to have to deal with each Anderson separately. You could just slide them all into each other, and then it becomes really easy to unplug and replug as a pack. These are the Anderson crimpers. They have really big lever arms, so it's easy to crimp. And the little block on the back here, it's hard to see in the photo, but there's a block on the back of it which catches the crimp for you. So you can just stick the crimp in and then crimp the cable. It makes it a lot easier than most other crimpers that we use on our team. Yeah, so this is a motor controller. You guys have probably seen this before. This is a Talon FX, I believe, or it's a Victor SPX. I can't really remember. But we use Andersons here, so it's easy to unplug and replug. It makes our entire system modular and thus need less soldering. Over here we use our signal connectors, which are these. We're moving away from these, but they're basically the friction fit connectors that fit into the Spartan board. They're really convenient, and you can't pull them out as easily as the old connectors that go on the Rio. So,
yeah, there's a little ridge on there that will lock in with the other side of the connector. So.
Yeah, so this is how we connect our Andersons. We try to make sure that we get the insulation all the way up to the end, so that way when you bend it, that doesn't just like, it's not too flexible at the connector end, but the rest of the cable is. This helps making sure that like you don't accidentally pull out your cables, or they don't break, or you just don't have exposed copper on the robot. These are butt connectors. They're really useful. You can use them as an inline crimp to connect two different wires together. We mostly use these for our higher gauges simply because they have really big holes. And we use these crimpers. What they have is a little bump in the center which pushes down on a little dimple in the middle which kind of squishes it together. So. And these are signal connectors. We're moving away from these, but these are really convenient for storing. This is what crimps go into those white connectors that I passed around. I believe if you go to the next slide, we might have a crimped version. Yeah, so these are what the crimpers look like. They also go into these housings. And okay, this is going back onto crimping. So, when you're crimping, there's a few things that you should keep in mind. So there's a few terms that we should probably get up first. There's the conductor brush, which is the wire, right? There's also the two buckets that I like to call them, the insulation bucket and the wire bucket, or the wire brush bucket. You want to make sure that you don't have wire brush in the insulation bucket. You also want to make sure that you don't have any insulation, or that you don't have too much insulation underneath your conductor crimp. Because if you do, then that causes the conductor crimp to not go fully down onto your wire, which means that you just have a poor connection. You also, and if you have too much wire, then the insulation crimp won't go down all the way, and you'll have a really flimsy connection. So this is a question for you guys. Based on what I explained, which one do you think is the best?
Go ahead.
Hmm?
On the right?
This one? So, close. You're two off. The left one. So, the reason is, I realize that there doesn't look like there's much difference, but generally, when you have insulation going all the way through, then you know that if this isn't ballooned upwards, your insulation crimp, or the wire crimp, can look like two things. It can look like this, which means that it's all the way down, or it can have like a little thing going up on the side, because some insulation got caught underneath it. And,
so the middle one's actually the best.
Exactly, because you can still see the wire, but, there's not any wire sticking out of the back, and it's crimped down all the way. Another common issue that I've seen is sometimes your crimper just doesn't work well, and you've gone one gauge up, or one gauge, you've gone one size too large, when the crimper doesn't crimp down all the way. Sometimes multiple crimpers can do that. Like for example, this has two. You can go one size up, and then you not have enough of the crimp going down. That would cause it to be too loose. A great way to test that is to just pull test it. You just grab the crimper with one hand, grab the wire with the other, and then depending on what wire it is, you'd pull it with a certain amount of strength. Like, for example, a signal cable, you wouldn't pull as hard as a power cable. You wouldn't pull a power cable as hard as you would a battery cable. You have to understand what cables would be experiencing what kinds of forces. And this is what it looks like when it's inserted into the housing. The crimps themselves have a little flap on the back that gets snapped into here. It's really difficult. You literally can't pull them out if you wanted to, which is really nice. Because you can still... I obviously wouldn't recommend this, but you could pull on the wires and it wouldn't take out the thing from the board. Instead, it would just take off the housing. And it's also really strong, even for just a friction fit.
Okay, so when the RoboRio first came out, we were looking at the kind of connection it could make, and this would be just what we call strictly a friction connection. And what people were doing to make sure the connectors wouldn't come out, they would use hot glue to reinforce it. Well, that's a mess. We didn't like that at all. So the very early thing the team did was develop the Spartan board, which allowed us to map all the connections to these Molex connectors, which have a little locking feature in addition to the friction fit of the female cable going onto the male connector itself. This board too also, at the time we wanted a 5-volt regulator and a 12-volt regulator because we weren't confident how well the power was going to be reliable coming out of the Robo Rio. Since then, our confidence has improved, so the next generation, you see, we dropped that off. But the other thing the board did as well was it mapped out the center connector in the Robo Rio. If we go back here, it allowed us to get to all the signals here and also break this out as well. So we could connect to the SPI interface as well as the additional digital and analog connections you have from that connector. Okay, so we can pass this around. Now what we're doing this year is we'd like a connector that locks better than the Molex, this version of the Molex. Okay. We're now using the SL system for Molex, and not just, there's a variety of SL connectors. We're using the ones that allow us to do a lock. Okay, so you can see how when I pass this around, how a connector can slide in and lock into place. And so we increase our reliability of the connection and lower the risk of a connector being pulled out during the competition. And like I said, we now have greater confidence in the power coming from the Rio. We're no longer providing our own 5 volts. We're using that coming from the Robo Rio itself. Here, let's go with this.
Not modifying the Rio's power also allows us to avoid the first certification step where you would have to get your board certified by first as you're dealing with cost power electronics and modifying them.
Yeah, so you can see how this connector system can work. This end has a device that will lock into this end. This is the connector side we have on Robo Rio, and this would be the cable side, and then you can release it by pushing down on this to pull it back out again. Yeah. And then it gives us a variety of connectors we can put on boards. We can do a vertical connection, we can do a right angle connection, and we can do a surface mount connection if we need to on the board side. And then lastly, it gives us a cable-to-cable connector possibility as well. So that we didn't get with the white Molex. Okay.
Question.
Go ahead.
So the Spartan board isn't adding any, like, doesn't have any custom PCB or any other electric. It's purely to allow you to use the type of connections you want.
Okay, so so the Spartan board, the question is, do we have any extra circuits on it, right? So the first generation we actually put a little IMU on it, and we had the extra power generation. The new generation is strictly passive. Okay, so there is no additional electronics on the board itself.
So it's purely to like
Purely get to the new connector system and also to map out the signals you get from the center connector. Right?
It also makes it a lot easier to manufacture in-house because even though we have a method for like reflowing the resistor and more complex components, it's just a lot easier for like a new member, say, to get into it and start soldering the connectors on. Another great part about the SL through-hole connectors is that they have these little posts which snap in, and you don't need to worry about them falling out while you're soldering. That's these two things right here. They just click in, and then you can start soldering, and you don't have to worry about like the 90-degree angle part of it.
Yeah, so in order to get to these signals here and easy access to those, that's what the passive board allows you to. So this breaks out the SPI from here, and then these, there are extra connectors, extra digital connectors that are coming out of this, mapping out of this connector as well, using the same connector style that you would otherwise use. Yeah. So going on to the battery, so we've been using the MK for a long time, and one of the reasons we like this battery is it actually, on the data sheet at least, has a fairly low internal resistance, 12 milliohms or 0.012 ohm, and the importance of that is that equivalent resistance is your voltage drop created by the current you're drawing times that resistance. So, which means the lower the better, the more voltage you'll get supplied to your robot. And notice here it says maximum discharge current for 5 seconds, 270 amps. Okay, well, this is in fact what happens. So this is a typical match that we've had with the robot. And you can see you got a current surge almost up to 300 amps just from running the robot. And then a lot of peaks in the 200 to 250 range. And what that does to your voltage now, you can see the anomaly of a 12 volt battery, but where we got that almost 300 amp peak, the voltage dropped on the battery below 8 volts, almost to 7 volts. Okay, so that's the importance of trying to choose your battery right. And then there's the issue of how you charge it. We've, in the past year, changed how we've been using the charger that we've used. Gone with this one because it's more designed for lead acid batteries actually, and actually has a AGM mode, which is the kind of batteries that we have. So this is really was designed for charging lead acid batteries. In addition to this, it has this repair function, which there's a little bit of controversy about how well this works, but it's intended to desulfate lead acid batteries. You know, batteries get old or they get abused, or you allow the charge on the battery to get too low, you can start creating sulfate problems in the battery, and this reportedly will help correct that. And my experience has been, I've tried this on our older batteries in the past year, and first characterizing the batteries and running the repair function and then characterizing them again, and it does make a difference, especially the older the battery, the more difference you can make in terms of improving its performance. Well, this only time will tell though how well that works for us. Now, this past season we've been using these chargers and we haven't had really a battery problem at all.
Yeah.
So it's been working out real well for us, I think.
Yeah, so the status LEDs up here let you know like what their charge progress is. I find this feature very nice. You don't need to press like restart to start charging the battery again, and it keeps the battery at like 13 volts or whatever its maximum is. And the green light here just tells you whether or not it's still charging or charged. And if it's down here, then you know that it's not usable at all, which is very useful.
Yeah, one nice thing about this is once you set up the charge in one way, it will always return to that same position next time you plug it in. So the other chargers we used to use, you always had to go to the menu, set it up, turn the charger on. Here, the moment you plug in the battery, it just starts charging the way you had set it up the time before.
What's the life of a battery?
Yeah. So the question is, what is the life of the battery? So we still have 2017 batteries that we'll use, but we'll think 2016 is getting old in the teeth. There's a belief that the newest batteries aren't necessarily at their best performance yet. So a year older or maybe 2 years older.
When you say performance, what do you mean?
Well, this is a little superstitious, but the ability to provide maximum power, basically, max voltage at the max current that you draw. Okay. What you're trying to avoid is having the voltage drop too low, so your essential electronics don't function. We haven't seen that event happen at all this past year, so that part's been good. But So one thing I'm not showing here is the team acquired a battery analyzer. Okay, so with the analyzer I can draw up to 80 amps. Okay, and I use it to characterize the batteries, right? So I create a program that simulates a match, and I use that same program on every battery. Okay, and then with that I can do a linear regression to generate equivalent series resistance for the battery, and use that to compare batteries. And when I did that, we had like over 30 batteries. That's more than we need. I was able to grade them and retire 10 of the batteries. Okay, just based on characterizing them with the analyzer and giving them a grade. So,
how often do you do that?
well, I did it before the season. Okay, and I just let the season go on, right? Especially with the repair function, I'm a little leery about it. I don't want to repair batteries too often because I was looking on a scope what it was doing. It was like applying 15 volts in pulses to do this thing, and that's, I don't know, a little queasy about that. Okay, but so my plan now is after we do our last off-season match, which is going to be Madeira in a week from now, then between that and before the next season starts, I'll go through and grade the batteries again. Maybe the older batteries I'll put through the repair function and see what we do. And then, since we always buy new batteries in the beginning of the season, I'll decide to retire the number of batteries that we're buying new quantity with.
What's the range, keep versus discard?
So when I do this grade, I'm sort of looking at two things. One is, what is the minimum voltage it ends up with? The higher the minimum during this analyzer session, this match simulation, the better. And then the ESR, the series resistance, the higher better. I mean, the lower the better. So if it's above 20 milliohms, for instance, I'm going to get rid of that battery. So I'm looking for something that's in the 1817 at least milliohms for my extracted ESR. Yeah. Now, because we have battery cables and contactors, we don't get 12 milliohms that the datasheet shows. We never measure that. Okay. But typically we'll get around 16, 17 or so. And it's a funny number anyway, because as you discharge the battery, the voltage is going down, right? So this, you can't truly call it the series resistance because I'm taking all this data, doing a linear regression to, extrapolation to, and I'm sort of fighting what else is happening with the battery. So, but it's useful to compare batteries, and the point here is let's keep 20 batteries, as we have 2 battery carts that can do 9 batteries each, and retire the ones that aren't as good as the rest. So, okay. Okay, so in summary here, you can see from what Het was explaining, we have a lot of elements on the robot. And the way it works is you can't really have a failure, right? Because it's not only embarrassing to the electrical group if the robot fails because of a connection, it's just not one of those things, I should say, you can tolerate, right? If you're designing to the maximum a mechanical thing and it happens to break and you had to trade off between weight and strength, that's one thing. But electrical connection has just got to be right. That's just the way it works. And for us, what we're trying to tell people, train people, is attention to detail, getting the crimps just right or the connections just right. It is important because we can't really tolerate a failure. Okay. Yeah, and so resources is for us and I think for any team. Of course, electrical mentors should be able to teach this. Student electrical leads, well, Het has been leading an electrical team, and he's actually very good skills with especially crimping and does a very good job of training other people. We hope to use this presentation actually now as a training medium in the future. That'll bring up students up to speed. And of course, the game manual from every year also gives you a lot of information about what you can do with the wire gauges, what you're allowed to do, and so on and so forth. So, okay, any other questions? You have any closing thoughts yet?
Yeah.
Oh, I'm sorry.
For can, how do you wire that? Do you use like standard daisy chain or do you use can hooks too?
Sorry, what was the second thing?
For the can, do you use like standard daisy chain or are there can hooks involved? Like how do you decide how to wire your can?
Repeat.
So the
repeat the
question is,
Yeah.
what does our CAN network look like? Right now, we just use the daisy chain. We haven't had any reason to do anything more complicated than a daisy chain. We don't use any CAN hubs. Yeah, we have one termination resistor at the end. I think the one special thing that we could do, or that we do, is we have a status light at the end, and if that isn't on, then we know that our CAN network isn't working. It helps because if there's only one thing at the end, then you know, like, hey, that part's broken, that means everything else is broken.
Yeah, so on this robot, we terminate at the Robo Rio, and then we have this can run, what do we call it?
It's the CTRE candle.
Yeah, and so the other termination is here. Okay, and so we're daisy chaining from the Robo Rio all the way up to that.
Yeah. and-
I've heard of teams that will do a star configuration and get away with it. Okay, but the CAN bus was really designed to have two end terminations and daisy chain between.
Yeah, so for our system in particular, we don't use solder connections in between. We just use Wago splices because it makes it a lot easier to swap out individual components or verify that your network works using a multimeter. And we also run it through the PD board just so that you can get the current data that we showed you earlier.
The reliability advantage of doing a star?
Well, yeah, so they do it because if you have a connection break, you're only losing one thing, right? So that's, but you know, the other thing to bear in mind, we use PWM heavily, right? So all our drive motors are PWM controlled, not CAN bus controlled. So we have a limited number of devices that are on the CAN bus right now. But the truth of the matter is the way the robot is designed and the way the software works, we can't have a failure anywhere. Okay, so yeah, Star's more reliable, but it doesn't really help us. Okay.
Yeah.
So you talked about designing your own version of the limelight. Do you think yours worked better? Or like, was there a electronic reason behind that?
Yeah, so the question was, we talked about designing our own limelight. What were the reasons behind that? The primary reason we did that is because we wanted the reliability that comes from making it ourselves. And we also saw a noticeable performance, noticeable performance improvement, not in terms of like software performance, but in terms of like what came out of it. I'm not entirely sure what Limelight gets, but we have about 2 centimeters of like radius and into knowing where we are based on only the goal, which is kind of amazing. And that's from just a single photo. If you combine that with the rest of the localizer using the IMU and past data, it becomes even more precise. So if you guys are familiar with what a Kalman filter is, in this case, our IMU is our noisy but higher frequency sensor. Our lower frequency sensor, but much more accurate, is our camera. The other thing is that we also had a really nice system for our Pis, so that way they could already interface with the light that we made, and it just works. Any other questions? It could also be mechanical, and how that interfaces with electrical. Yep.
Sorry. How do you decide like where to put your electronics? Does that design come in, or do you design the robot with the electrical components in mind, or do you like find a place to put them after?
Mm-hmm. So the question was, how do we design our electrical systems, and does that come during the design process, or does it come after? Most of the time during the design, it's kind of an afterthought mechanically. They give us space, and we have to use the space. In this case, we had the entire belly pan to ourselves. In 2019, that was significantly more cramped. For those of you who don't remember, our robot was small. This robot is significantly larger. And we tried to keep like components together. Like, for example, the networking was all on one side. All of the signal stuff was on the other. Like, the PD board was next to the Rio. Another thing that we also do keep a lot more in track of is where the main breaker is, where the PD board is, and where the battery connector ends up. Because that determines what battery cable lengths we need. And that's the one thing that we have to rely on. Because we keep our battery cable lengths all the exact same, or at least within like an eighth of an inch.
Mm.
So it helps us that we know exactly where that's going to end. And in this year and like the past 2 years, our robot was underneath our battery was underneath our robot. So that was a fun design problem.
Yeah, so actually on the batteries, what you really want to do with the batteries, you want it to be as low as possible on the robot, because you want the center of gravity in your robot as low as possible, and the battery is heavy, so you can use that to your advantage. And it's because of that, that's why we often end up with a bottom axis battery, because that's gets you the battery in the lowest part of the robot.
Yeah, and another interesting thing that we did with our power is we made one of our motors this year right next, like with an Anderson right next to the PD board, so we could connect it using a power supply. It allows us for like extended testing. You don't have to swap out the batteries, so this is just really helpful for us. Like for example, during shot tuning, or if you're just prototyping the software in a specific intake or whatever, it's really handy. So I suppose I can walk through more about the robot. Let's see, microphone. Okay, so robot. A few special things that we've done is, at least on the new Robo Rio, wherever that ended up. You guys might remember me talking about the combination encoder, the mag encoder and pot combo. That just gives us a nice absolute zeroed intake, or joint. Oh, an interesting thing that you guys can think about is everything is an intake. Like the catapult is just a very fancy intake. The turret is also a very fancy intake, because to software they all look the exact same. Software doesn't care whether it's a turret, intake, or catapult, because it has the exact same sensor combination, it has a motor, and it has a gear ratio, right? And we decided to reflect that electrically. We made a connector which has the mag encoder digital, the quadrature A and B, and and an analog input. So that way we could just combine all of them into one and then plug it in here. It just makes it a lot easier to handle electrically, because we can just plug in one and just be like, oh, well, we know we have an intake somewhere on the robot. It's really helpful. And another thing, we used servos on the robot this year. To power the servos, we used the Rev power module for servos. It's not very visible, but it's right here. We just used 18 gauge wire coming off of the PD board for the 30 amp slot. It didn't take up much power. It was pretty easy to put in. We didn't put in any hot glue to hold it in, because we didn't see any issues with that. We also really like our zip ties, so wires probably wouldn't have come out. Another thing, potentiometers. We've made custom PCBs this year that soldered directly onto them. So that way you can just, and it has a connector built into it, so you can just unplug and reconnect the connector instead of having to solder on the pot each and every time. Okay, now that I've said things, do people have more questions? Okay.
Oh.
Yes.
You talked about the Lego connectors
Yeah.
already, right? Okay, sorry.
Yes. Oh.
What did you use your servos for last year,
This year?
or this year?
Yeah, so we used our servos for the climbers. This is our passive climber. I realized that was a bit scary, but it's a constant force spring coming up here. And the idea is that it pulls it up. So I realized I pulled like a magic button and that caused that to happen. But basically the servo latches into here. It's not at the right height, but it latches into here. And what it does is the constant force spring releases, pulls up, and then you have that. We use that to get to our high bar climb. This disengages, and then we swing forwards. It's surprisingly load bearing. We also use Teflon tape to reduce the friction so that way we can have this sliding component without it getting jammed. It's kind of hard to see it, but it's right here. You guys come up after the presentation. Further questions?
So you'll notice we use the older PDB board on our robot. A lot of people this past year went to the Rev Robotics PDB board. We stayed with it for a couple reasons. One is we had them, okay. The second is they're actually smaller, this one, and so it's, in this robot I'm not sure we could have fit the Rev Robotics, or at least we'd have to orientate things differently. We also didn't want it to be using the Rev Robotics the first year it came out, because inevitably there can always be bugs, right? But there are a lot of advantages. You have to use a special tool or a screwdriver, know the technique with this current PDB board in order to get the wires in and out. And it's one of these skills, I guess it takes a little while to figure out how to exactly do it. It's like a push in, rotate all at once, and then you get it to open up. Of course, with the Rev Robotics, they now have levers, so you don't need these tools anymore. So that would make it a lot easier. That'd be a good reason to go with the new one, the Rev Robotics. I also found, actually, too, you saw that I had this match display of the current throughout the match, right? We're getting that from the PDB board. I found this year's PDB board that it was slowly giving me different answers or failing as the season went on. I was getting constant currents when they wasn't drawing currents, reporting that, so we're going to have to replace these items, or hopefully maybe the Rev Robotics will be better in terms of giving us consistent data. So whatever. I'm hoping we'll use the Rev Robotics this year on the robot, and I hope the increased size won't be an issue for us.
Yeah, the other advantage that I've noticed without using it is everything is a 40 amp slot now, and that means that everything can move incredibly fast.
And it has more slots too, right? And
Yeah.
we have a habit of using up everything. We have a lot of motors. So I think this year we ended up using all the ports. And we're not doing a swerve drive, and if we did a swerve drive, it actually requires more connections than we get with the tank drive.
So one other interesting thing is these transfer rollers right here. They're both connected. They're both powered off of bag motors, and they're also both powered off of the same motor controller. We used to have two motor controllers, but then they took out one of them due to weight because we were saving grams for this thing to fit in. It was interesting. It's also surprisingly legal. I didn't realize that you were able to do that. One interesting thing there is that you can make Y connectors using Andersons, but we had to use our alpha wire or eco wire. That was that ridiculously thin stuff. 12 gauge is thinner than 10 gauge, and it was thin. And it worked too. And if I spin this hard enough, you can see that one switches too, because it's connected. So yeah. Any other questions? Could also be about random things that are on the robot that you guys don't exactly understand. Yeah. Oh.
So your custom electronics, what makes you decide what needs to be custom or what you just want to get off the shelf?
So the question was, what needs to be custom, or what do we choose to be COTS? To be perfectly honest, custom electronics are like a what if we did this kind of thing. Sometimes it was born out of necessity. Like, for example, the Pi Power boards. I can't really show it to you because it's underneath the tape. But the Pi Power boards were because we needed a way to power our Pis. And we also knew that we couldn't just power it off of USB-C because that is unreliable at best. And it's also a lot easier to break a USB-C connector than it is to break a ferrule. So we made this in 2020. And then we switched to a different EDA software, and now this is in a deprecated, nobody uses it anymore EDA software. That's something that we need to change. The light ring, we could have made, again, using COTS components. We made it ourselves because we sprinkled in a few more features that we really liked, like being able to being able to vary the brightness using a PWM input. We also were able to put its own power controller in there. So I was able to boost the current to what it needed, voltage to what the LEDs needed. It's also redundant, meaning that each of the 4 quadrants of the LEDs are powered separately. So let's say if one of the quadrants broke, you would still have 3 more. So yeah, we have a very why not attitude on this team. We also have the people and time to do this. Oh, yes.
Oh, did you cover limit switches, and do you wire them normally closed or normally open?
So the question was limit switches and how do we wire them. We haven't had limit switches on this robot, and we haven't had them the last year I was on this team and had a robot, but he knows better than me.
The reason why that came to mind was in the other presentation they talked about at Chesney Champ, your limit switch for the turret failed, and it turned and ripped everything out. And so in industry, what you would normally do is you wire up the limit switch to be normally closed, and when they open up, then you get the trigger. And so in the event the limit switch fail, then your thing don't work.
So there's no hardware limit switch. What they were mentioning was a software limit. Yeah, it's a software limit. So in this case, the pot failed. It broke off.
So there's each team has their little prejudices. Okay, and our team, due to mentor history and so on, we do not like limit switches. Okay, because there's a belief or a superstition that they fail. Okay, so we don't. I haven't seen a robot in my 12 years with a limit switch on it. Okay, we just avoid them, and so you notice we have potentiometers. So we have potentiometers and mag encoders. They're used together in software to make sure software knows where things are, and if they're not where they're supposed to be, then it shuts down, right? It doesn't operate the mechanism. So that's how we do our limit testing. But we don't have the physical limit switch because I think some of the mentors who were members on the team used limit switches at one point, and they got burned badly by it. And so experience creates superstitions, and ever since then we've never used a limit switch. Okay.
No, but do you understand what I meant by normally open and normally closed?
Yeah.
Then does the audience know that? So that if the actuator gets to its limit, do you want it to activate the switch or deactivate the switch? So if you have it to deactivate the switch, that means that if the switch ever fails, the operation won't work, which is actually better than having a limit switch that activate and there's a broken wire and it never gets activated, and then things break.
Yeah, that makes sense.
And then with the potentiometer, I think they can still do the same thing in that in the event that the potentiometer wire breaks, do they look at that connection in your analog input and say that's an open circuit and therefore stop?
Due to the way how the Rio works, I believe it just floats. It doesn't actually bring it high or low in the case of a wire failure. Also, the case here wasn't a wire failure, the pot was disconnected entirely. We're still not entirely sure how that happened. In the same match, the top half of one of our optical encoders also just disappeared. That's one of the unsolved mysteries of this robot.
But still, electrically, you could still make that input float by having a pull up or pull down resistor, so that in the event the potentiometer wire fails, it'll pull up or pull down, and essentially software will look at it and say, hey, wire broke, therefore shut down, instead of.
Okay. Well, yeah.
I mean, I came from industry, and they do that in heavy equipment, is that they don't rely on a switch activating when you hit the limit, but the switch deactivating. So, if a wire breaks, the system don't even work, and then you have to go, and it's a pain to go troubleshoot it too, but you know.
Okay. Well,
Anyway, that's just a,
no, it's a good point. It's a good point.
It's a good point. It is also 333.